Hello friends, so today in this video we are going to talk about heat transfer through the infinitely long fin. In the previous video I have did an analysis on heat flow through the rectangular fin. So I have given a brief description about all these 3 points for the heat transfer through the infinitely long fin. Heat transfer when the end of the fin is insulated and when fin is of some finite length. Okay, so I'll discuss infinitely long fin in this same video, and in the next videos I will discuss about these two topics. Okay, so let's move on to the topic heat transfer through the infinitely long fin. Okay, so when the length of the fin is infinite, so L tends to infinite. Okay, heat transfer through the infinitely long fin. Okay, so let us see its 2D diagram. Okay, we are not going into the 3D diagram of this same rectangular fin. So say this is infinitely long fin. Okay, this gap may be, I don't know how much this gap is. Okay, so this is x equal to L equal to infinite, this is x equal to 0. So there are some boundary conditions that we are need to consider in this topic. Okay, so first of all let us draw a diagram or graph that will make you understand that how much variation would be in the temperatures. So this is a graph for temperature with x. Okay, so this is T, this is x axis, and now the temperature at the base is maximum, so T at this x equal to 0 is maximum T naught, and here x equal to 0, and this is T ambient. Okay, or the T atmosphere. Now what happens when the distance increases, the temperature decreases. Okay, so this is the graph like this, parabolic. Okay, now there are two boundary conditions that are need to be considered in this topic. That first one is at x equal to 0, what would be the temperature? Temperature would be T naught. Okay, and when x equal to infinite, temperature would be ambient temperature, so it would be Ta. Okay, so when x equal to 0, we know that theta is equal to T minus Ta. So when T is equal to T naught, then theta would be equal to theta naught, T naught minus T ambient, and same for this T for x infinity, so theta would be equal to Ta minus Ta, so it will be equal to 0. Now let us apply the boundary conditions. So already we have a equation that we have derived in the previous derivation, theta equal to c1 e raised to power mx plus c2 e raised to power minus mx. So from this, now applying the theta is equal to c1 e raised to power minus mx, sorry, plus mx plus c2 raised to power minus mx. Okay, now when we'll apply the boundary conditions over here. Okay, so let us put the value. First of all, we'll apply the second boundary condition. So when x equal to infinity, so theta would equal to c1 e raised to power m infinite plus it would be 0, so c2 e raised to power minus m infinite, so it would be equal to c2 upon e raised to power m, something like this, e raised to power 1 upon e raised to power m infinite, so it would be equal to 0. And at x equal to infinite, we have theta equal to 0, so this would be equal to 0, c1 e raised to power infinite plus 0. So from this we will obtain c1 equal to 0. Okay, now applying first boundary condition. So when we'll apply the first boundary condition, we'll obtain again theta equal to c1 e raised to power mx plus c2 e raised to power minus mx. Now when x equal to 0, theta equal to theta naught, so theta naught will be equal to c1 e raised to power 0 plus c2 e raised to power 0. Now from the previous equation we have the value of c1, so c1 is 0, that theta naught equal to c2 e raised to power 0, that would be 1, so c2 equal to theta naught. Now when we'll put the value of c1 and c2 in this equation, then what we will obtain? So putting these values in above equation, so theta is equal to c1, at the place of c1 it would be equal to 0, so 0 plus theta naught e raised to power minus mx, and again theta upon theta naught equal to e raised to power minus mx. So this is the final equation that we obtained, t minus ta upon t naught minus t equal to e raised power minus mx. This is the very important formula in the case of these questions. Okay, if we have any two of these, then we could easily find out the ambient temperature or the temperature at distance x. Okay, so this is temperature at some distance x, this is the ambient temperature, and this is the temperature at the base. This is the value m and this distance x. Okay, so if there is any term is missing, then we could find it out. Now we need to find out the heat transfer. Okay, so for finding out the heat transfer, we need the Fourier's equation. So from the Fourier's equation, we have q equal to minus ka del t over del x. Okay, now in the previous video, I have discussed to you about how do we obtain dt over dx is equal to d theta over dx. So you can either check it out. Okay, so or you can remember this, that there is no difference in these two. Okay, so just put these values ka d theta over dx at x equal to 0. Now again here theta is equal to theta naught e raised power minus mx, so minus ka d over dx theta naught e raised power minus mx. Okay, and at x equal to 0. Now again after solving this, what we will obtain minus ka theta naught e raised power minus mx, and here minus m would be taken out, so minus m at x equal to 0. Now we could apply this condition at x equal to 0, so when x equal to 0 it would be equal to 1, so m ka theta naught and m minus minus will be cancelled out. Here we have m is equal to under root hp upon ka, so q would be equal to ka theta naught under root hp upon ka, so it would be equal to k would be cancelled out, so it would be hp ka whole into theta naught, and this is the final equation that we need to obtain. Now almost this topic is over, but we could draw a curve, a diagram for this equation. This is the dimensionless temperature, this is called dimensionless temperature, and we could find a relation between this value m and this dimensionless number. Okay, so what would happen if we will increase the value of m, then what will be the effect on this dimensionless number or theta upon theta naught. So let us see in the diagram. So let's say this is a graph, and this is theta upon theta naught, and this is x. Okay, now say there are three values of m. Okay, now when we will increase the value of this theta naught, the value of m will decrease. Okay, and we will increase the value of theta upon theta naught, the value of m will increase. Okay, so there is vice versa for this. So this is m1, say this is m2, and say this is m3. So lower the value of this, higher will the value of m. So m3 is greater than m2 is greater than m1. So here m3 is having the bigger value of all three. And this is it. Thank you for watching. If you like this video, then give a thumbs up and share this video. Thank you for watching.